In recitation this week, we're going to get ready for Exam 3. Exam 3 covers Chapter 6 and Chapter 7. We looked at the nature of light, understanding the relationship between frequency, wavelength, and energy, understand the photoelectric effect, understand the origin of atomic emission spectra. And then we got into Chapter 7 where we talked about quantum mechanics, which basically presented us the orbitals that we know today, the shape of those orbitals, the number of orbitals, the electrons that we can hold in those orbitals, so electron configuration of atoms, electron configuration of ions. And then from there, we got into periodic trends, talking about the trends for atomic radius, ionization energy, and electron affinity. So I know this is the same slide from last week, but just to, reiterate the importance of understanding these two equations and the relationship between these two equations, understanding the relationship between frequency and wavelength and frequency and energy, and the fact that we can combine these two equations and also be able to relate wavelength and energy. And then using these equations, understand what this means for the visible region of the electromagnetic spectrum, what it means for blue light versus red light, for example. So blue light has a shorter wavelength, higher frequency, higher energy. Red light has a longer wavelength. Longer wavelength means lower frequency, and a lower energy. So just from thinking through those relationships in the equation and not necessarily doing a calculation. And then this week in class, we talked about the periodic table, electron configurations, electron assignments, and we broke down the periodic table into different regions where we talked about anytime we're working through this region in the periodic table, we're filling s orbitals, right? Not to forget that these numbers here correspond to the quantum number of each of those orbitals. So this is our first quantum level, right? I have an s orbital. My second quantum level, I have an s orbital, and I have p orbitals, right? Third orbital, third quantum level. But back to the regions, right? Anytime I'm working through here, I'm filling an s orbital. I have one s orbital at every energy level. It can only hold 2 electrons. So 1, 2, it's full. 1, 2, it's full. Over here are my p orbitals. Right, I have 3 p orbitals, 2 electrons each. So 1, 2, 3, 4, 5, and 6 electrons total in those 3 p orbitals. And then again, once that's full, we start over to new quantum level, so the third quantum level, right? Anytime I'm working through here, these are my d orbitals. I have 5 d orbitals per quantum level of the third quantum or higher. 5d orbitals, 2 electrons each, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, for a total of 10 electrons in my d orbitals. And then if we're down here with the lanthanides and actinides, right here are f orbitals. I have 7 total f orbitals, 2 electrons each, for a total of 14 electrons within each of these f orbitals. So here are some questions for you to kind of review those main calculations. Some of this is similar to what we did last week, but this is these are the key equations that we should know before the exam. So what is the energy in joules of 1 photon of light emitted from a green laser pointer that has a wavelength of 584 nanometers? Well, the first step for this calculation would be to convert 584 nanometers into meters. So I'm going to multiply by, for every 1 meter, I'm going to have 1 billion nanometers. So I'm going to have 5.84 e to the negative 7 meters. And now I can directly go from wavelength to energy if I use the equation energy equals Planck's constant times the speed of light divided by my wavelength. So for this calculation, my energy equals Planck's constant 6.626 e to the negative 34 joules times seconds times my speed of light 3 e to the 8th meters per second, all over my wavelength that I just calculated, 5.84 e to the negative 7 meters. Take a look at the units, and for the units, right, meters will cancel out, seconds will cancel out, and that's good because I'm looking for units of energy, I'm looking for units of joules, and I should get about 3.40 e to the 19 joules, e to the negative 19. Three significant figures because the only thing that's measured here is three significant figures. Planck's constant's a constant. That does not influence our calculation in the significant figures. The speed of light is also a defined value. That does not influence our significant figures either. Here's another question of that type for you. The wavelength of an X-ray is approximately 10 nanometers. What is the frequency of this wavelength? And then how much energy would be contained within a mole of photons from an X-ray? Well, much like our last calculation, the first step is the same. The first step, I need to go from 10 nanometers to meters because I use the speed of light in meters per second. So I need those units to cancel out. Well, I know in 1 meter, I still have 1 billion nanometers. So I'm going to have 1.00 e to the minus 8 meters. And now the equation I want to use is speed of light equals frequency times wavelength. We know wavelength, we want to find the frequency. So to rearrange this equation, right, frequency equals the speed of light divided by my wavelength. So my frequency equals the speed of light, 3 e to the 8th meters per second, over my wavelength, 1.00 e to the negative 8 meters. And I get approximately 3 e to the 16th inverse seconds. That's my frequency. Now to find the energy, I know energy equals Planck's constant times my frequency. Energy equals Planck's constant 6.626 e to the negative 34 joules times seconds times my frequency that I just found from the previous calculation, 3 e to the 16 inverse seconds. I multiply, seconds cancel out, and that leaves me with energy. Energy equals approximately 1.98 e to the negative 17 joules. Now to find the energy for a mole of photons, well, this is energy per 1 photon. So I know that in a mole of photons, I'm going to have Avogadro's number, 6.02 e to the 23 photons. Right, Avogadro's number, to have a mole, you're going to have Avogadro's number of that item. I multiply by Avogadro's number, and the energy ends up being 1.20 e to the 7 joules per mole. And to put that into context, right, when we were calculating the energy of UVA and UVB light, and we saw that the UVB light was around 300 kilojoules per mole, right, on the magnitude of a bond, a chemical bond, right? If we put this into kilojoules per mole, this ends up being 12,000 kilojoules per mole, right? So that's why when you go and get an X-ray, you use a lead vest to protect you from that energy of an X-ray. And the last review calculation of this type, we talked about how MRI imaging is used and the wavelengths of MRI imaging. So the MRI imaging works on a frequency of about 300 megahertz. What is the wavelength in meters and energy of this signal? So the first calculation, we want to find the wavelength of this, but I'm given a frequency. I'm given a frequency of 300 megahertz. And I need to know that for every 1 megahertz, right, megahertz is larger, I have 1,000,000 hertz. So that cancels out, so I have 3 e to the 8th hertz, which are cycles per second, inverse seconds. I can calculate the wavelength now because I know the speed of light equals frequency times my wavelength. Rearrange that equation. Wavelength equals the speed of light divided by my frequency. Speed of light is 3e to the 8th meters per second, and my frequency is also 3e to the 8th inverse seconds. So my wavelength is actually 1 meter. 3 significant figures in this answer because I have 3 significant figures here in the frequency. And then to calculate the energy of this, right, I know energy equals Planck's constant times my frequency. So my energy would equal 6.626 e to the negative 34 joules times seconds times my frequency from step 1, 3 e to the 8th inverse seconds. The energy of an MRI signal is approximately 1.99 e to the negative 25 joules. All right, now that we're into periodic trends, so one of the main periodic trends is atomic radii, and we know atomic radii, the two main trends, atomic radii increase as we go down a group, and atomic radii also increase as we go right to left across the periodic table. So rank the following atoms from largest to smallest. Well, the largest would be the farthest down a group, so the farthest down appears to be potassium, and also the farthest to the left. So potassium in this series would be the largest, followed by calcium, looks to be next from the 4th quantum level. After that, everything we have left is in the 3rd quantum level. So again, farthest to the left would be sodium, followed by magnesium. After magnesium, then we're working our way to the right in the periodic table. After magnesium, we would have aluminum. After aluminum, we would have phosphorus. And then last, we would have chlorine. So again, the farther we go down a group, the larger the atomic radius is. And then as we go from right to left in the periodic table, the atomic radius also increases. Rank the following ions from largest to smallest. This one's a little bit different, and we have to think about what happens when an atom loses an electron and what happens when an atom gains an electron. And so in this case, the question was made easy for us in that all of the atoms in question are in the same row. We've got sodium, magnesium, aluminum, sulfur, and chlorine. So when we gain an electron, we have a larger ionic radius than our parent atom. And sulfur is going to end up having actually the largest ionic radius because it gains 2 electrons. We're increasing the amount of electron-electron repulsion. Followed by chloride, followed by sodium, magnesium, and aluminum. For the cations, aluminum would be the smallest because we have the largest imbalance between the electrons and my protons. 3 protons more than the electrons, meaning that the protons that I have there can pull the remaining electrons closer to the nucleus. We also looked at condensed and full electron configuration. So for the electron configuration, right, we go to the periodic table. We know in the periodic table the orbitals we're filling and in what order we're filling those orbitals. So to take a look for magnesium, magnesium is in the 3rd quantum level. So to get to the 3rd quantum level, 1s2, 2s2, 2p6, 3s2 takes me to magnesium. For the condensed configuration, we go to the nearest complete noble gas. That would be neon. And then what electrons do I have after that? So my condensed configuration would be neon, 3s2. Sulfur is just a little bit farther out in the 3rd quantum level, so we still have 1s2, 2s2, 2p6, 3s2, 3p4, 4 takes me to sulfur. And then for my condensed configuration, neon is still the closest noble gas. So neon, 3s2, 3p4. Iron, we're down here now in the 4th quantum level. So iron, 1s2, 2s2, 2p6, 3s2, 3p6. That takes me all the way to argon, 4s2. And then remember, after 4s comes 3d. 3d6 takes me all the way to iron. Argon is my nearest complete noble gas, so I'd have argon 4s2, 3d6. Selenium's a little bit farther out in that 4th quantum level. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 takes me to zinc. And then I'm 4 more, so 4p4 takes me all the way to selenium. Condensed configuration, argon, 4s2, 3d10, 4p4. Yttrium is in the 5th quantum level. Yttrium starts like all the rest of them start, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6 takes me all the way to krypton, and then I would have 5s2, 4d1 takes me to yttrium. I can replace all of this by simply saying krypton, 5s2, 4d1 for my condensed configuration. What's the electron configuration for the following ions? Aluminum, magnesium, sodium oxide, and the fluoride. So here's aluminum, here's magnesium, sodium, oxygen, and fluorine. And then once you've done that, what is this group of ions known as? So aluminum ends up being 1s2, 2s2, 2p6, aluminum 3+. Because I'm atomic number 13, to be 3+, I'm going to lose 3 electrons. I need to have 10 electrons total. 1s2, 2s2, 2p6, that's 10 electrons. I'm isoelectronic with neon. Magnesium, 1s2, 2s2, 2p6. All right, magnesium 2+, atomic number 12, it lost 2 electrons, also has 10 electrons now, isoelectronic with neon. Sodium is atomic number 11, loses 1 electron, so 1s2, 2s2, 2p6, also isoelectronic with neon. Oxide gains 2 electrons, so atomic number 8. Add in 2 more electrons, and the only place I have room, 1s2, 2s2, 2p6 as well. Isoelectronic with neon. Fluoride, atomic number 9. I add in 1 electron, the only place I have room, 1s2, 2s2, 2p6. Isoelectronic with neon. And if we didn't know already, based on what I was saying, right, what is this group of ions known as? This is an isoelectronic series. All of these ions have the exact same electron configuration as neon. And the last 2 trends have to do with ionization energy. So the 2 questions for you. What is the trend in the first ionization energy as you move down a group? And the second question, what is the trend in the first ionization energy as you move left to right across a row in the periodic table? To answer that question, you just need to think about what is the trend in atomic radius and think about the electron as a little magnet and the nucleus as another magnet, and how close are those magnets together or how far apart are those magnets. So what is the trend in first ionization energy as you move down a group, right? down a group, the first ionization energy decreases as the quantum number increases, right? And that moves the outer electron, the outermost electron, farther from the nucleus. Farther from the nucleus, it's easier to remove that outermost electron. And then across the periodic table, the first ionization energy increases as the atomic radius decreases, right? Moving the outermost electron closer to the nucleus. Right, closer to the nucleus makes it harder to remove that negatively charged electron. So for the exam on Thursday, right, we need to know how to convert meters to nanometers and back and forth, megahertz to hertz, gigahertz to hertz, joules, kilojoules, conversions like that. Realizing that a hertz is equal to inverse seconds. Understanding what orbitals are available at each level, how many of those orbitals, each orbital holds 2 electrons, right? Electron configurations for atoms and ions, and then the last thing we need to know are the periodic trends within the periodic table that we talked about. Atomic radii, ionization energy, and electron affinity.